we're going to continue with chemical bonding here. Oh yeah, I was supposed to do that yesterday. I'll do that. I'm going to post that. You're going to start off with the supplement though. Homework. All right, with chapter 12, we're looking at bonds. So chapter 12 starts off forming ions, cations and anions from the elements. And so if we look at nitrogen, nitrogen's electron configuration is 1s2, 2s2, 2p3. And what we want is we want 3 electrons, and that would complete the valence shell. The valence shell would be the outer shell here, 2s2, 2p3. And so it has 5 electrons total, the 2 in the s orbital and the 3 in the p orbitals. So an additional 3 would complete it. So that's what happens. It gains 3 electrons, and it's going to form this N3 minus. This is the formula. This is what we call Lewis structure. Here's a Lewis symbol or Lewis dot structure. This is the Lewis structure for the ion. Lewis structure for the ion, when there's a charge, we draw square brackets around it. We show the electrons here. So now it has a total of 8 valence electrons, so let's fill the 2s2, 2p6 shell here. All right, this we say is isoelectronic with neon. Neon has 10 electrons. It's a noble gas here, and so nitride also has 10 electrons. Oxygen has 6 valence electrons. Nitrogen has 5 valence electrons. Let me see. Did I talk about Lewis symbols already? No. No. Okay, I'm jumping ahead. Lewis symbols we use just to show the valence electrons. So let's see. Here. This is back in chapter 11. All the alkaline earth metals have 2 valence electrons. And so if we look at the alkaline earths, let's start. Well, let's look at the alkaline metals. The alkaline metals first: sodium, potassium, rubidium, cesium, lithium. So lithium is going to have the 1s2, 2s1. Sodium is going to have 1s2, 2s2, 2p6, 3s1. Potassium is going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And so what we see here is we see the core, which will be filled here. This will be the core. This one is going to be the helium core with the 2s1. This will be the neon core, then 3s1, argon core, etc. And so another way of representing these is we could use the abbreviation for the core. This would be helium 2s1. This would be neon 3s1. This would be argon 4s1. And so all these have 1 valence electron. The remaining are core electrons. So core, valence here. And so when we look at the pattern is ns1. That would be the pattern, where n just varies. It would be hydrogen's 1s1. But we'll start here. 2, 3, 4, etc. ns1. And so it's got one total valence electron. We could show that one valence electron using the Lewis symbol. So lithium, we'd show that one valence electron. All the core electrons aren't shown, but the core electrons would be contained within the atom. Now, sodium would have the exact same symbol, except the core would be a lot bigger for sodium. So it's a bigger atom in general. Another shell electron. Potassium looks exactly the same. Rubidium, the same, and cesium. So all these have one valence electron.
So why is it NS1 if they each have two valence electrons?
Why is it NS1 if they each have two valence electrons? That's because I'm on a different slide. This is the alkaline earth. This is the alkaline metals. I skipped it, sorry. This would have one valence electron. So the same thing goes. If we look at beryllium, beryllium would have two valence electrons. It'd be helium 2s2. And then sodium goes to magnesium. Magnesium would be neon 3s2. And then potassium would be argon 4s2, etc. Go on. And so the alkaline earths, when we look at the pattern, the mathematical pattern there, it's all NS2, which means all these have two valence electrons. So beryllium, we would show two dots like this. Magnesium, we show two dots like this. It'd be potassium, sorry. Calcium, we would show two dots like this. Calcium. And so these were the alkali metals over here. These are the alkaline earth, all the alkaline earth. When we look at the Lewis symbol, they all are the same as far as the way they look here. We could do this for all the families. And so that was the alkaline earths, the NS2. If we look at the halogens, let's start off with fluorine. Fluorine's going to be a 1s2, 2s2, 2p5. And so it's almost filled, the p subshell. It's almost filled. It's just one electron short. But anyway, what we say here is, well, this is equivalent to helium 2s2, 2p5. Now for the dots, we aren't going to differentiate. Is that dot from an s orbital or is that dot from a p orbital? No, that dot's going to be from this, the valence. So if we look at the valence, there are going to be 5 electrons in the valence shell. The helium at the core. And so for fluorine, we would draw 5 dots. Not 5, what am I doing? 5 plus 2 is 7. 7 electrons, sorry. We draw 7 dots, like that. So that would be the Lewis symbol for fluorine. Chlorine would have the same. No, it would have 7. It's 1 electron. Except it'd be 3s2. This would be it. It'd be neon, 3s2, 3p5. And so all these are going to have the ns2 and p5, giving a total of 7 valence electrons. Now, what's going to happen is we'd like to fill that shell. If we fill that shell, fluorine would have to gain 1 electron, and then we could fill that shell, full shell. Here with chlorine, the same thing. With lithium, how many electrons would it take to fill that valence shell? It takes 7 electrons. It only has 1 electron. To fill the shell, we'd have to fill the 2s orbital and the 3 2p orbitals. And so 7 electrons. Will lithium gain 7 electrons? No. That's not likely. So as an alternative, we could lose that valence electron. If we lose that valence electron, we lose the 2s1 electron, we're left with the helium core. Helium core would be filled shell. Same thing with sodium. If we lose that electron, we're left with neon. So that's an alternate way. So we are either going to gain or lose electrons to be isoelectronic, which is near Nobel gas. And so let's take a look at this process of gaining or losing electrons. And, that's this formation of ions. Let's see here. So we're either going to gain or lose electrons. Well, if we lose electrons, we're going to form a cation. And so all these will form a cation because it's a lot easier to lose than to gain a huge amount. Same thing with these. The cations are positively anions if we gain. So when we look at it, nitrogen, if we look at the valence shell, the 1s2 of course, so if we look at the valence shell, it's 2s2, 2p3, so a total of 5 electrons. Those 5 electrons are going to be represented by these dots here. And again, these dots don't show if it's an S or a P, we don't really care. It's just going to be valence shell. So we have 5 electrons in the valence shell. Well, either we're going to get rid of 5. If we get rid of 5, we'll form a +5 charge, or we're going to gain 3. But getting rid of 5 might be difficult, so sometimes we don't get rid of 5. Depends on what your reaction is with. And so the charge for nitrogen ranges from +5 to -3. Excuse me. And so here it gains 3 electrons. We fill that outer shell and we form nitride ions. So this is the formula for nitride. This is the Lewis structure for nitride ions. Oxygen. Oxygen has 6 valence electrons. We want to complete that shell. To complete that shell, we need 8. 8 electrons is required to complete that shell. And so 8 electrons is called an octet. We want an octet of electrons. And so oxygen is 6 here, we gain 2, we get an octet. 2, 4, 6, 8 electrons here. This is Lewis structure, this is the formula for oxide. Fluorine wants to gain 1. So this electron configuration before, this electron configuration after, gains 1. This is the Lewis structure for fluoride, this is the formula for fluoride. All these have 10 electrons total. 8 electrons in the outer shell, 2 electrons from the core. Just like neon. In the outer shell, we have 8 electrons, in the core we have 2. So the outer shell here is filled, a filled shell. So neon doesn't want to lose or gain any electrons, so it's stable as is. Neon's a noble gas. Noble gases used to be called inert gases because they're so unreactive chemically. Well, these species want to gain electrons. These species want to lose electrons. It's a lot easier. So sodium has 1 valence electron. We lose that here. We're left with 1s2, 2s2, 2p6, 10 electrons, right? Just like neon. Magnesium has 2 valence electrons here. We lose those. We'll form magnesium 2+, 10 electrons, filled shell. And then finally, aluminum, with 3 valence electrons. We can lose all 3 of those and end up with the neon core that's left. So those are ions. Now, the whole reason for forming ions is to form ionic compounds. You know, that's why we want to form these. Not just for the ions themselves, but to form compounds. So these are the ions. This is just a partial list. This is the ions that are typically fixed charge ions. You know, group 1 are +1, group 2 are +2. This is group 3b. Group 3b is +3. Now, when we get to group 4b, things vary a little bit more. We get variable charge. We get variable charge until we get to group 1b and 2b. These are 1b and 2b. Did I talk about those already? Silver and cadmium and zinc. Then we get to group 3a here, or 13. Group 3A is fixed charge, aluminum 3 plus. Group 4, you know, group 4 is kind of in the middle zone. Group 4, we either want to gain 4, which isn't easy, gaining 4 electrons, or we want to lose 4. Losing 4 isn't easy either. But those are the charges. So something like carbon gains 4, we form carbide ion, loses 4. Loses 4 is tough because the carbon plus 4 isn't so stable. It could be stabilized by reacting with oxygen or something like that. So there's different ways to stabilize it. But here we have nitride, oxide, fluoride, and neon. Likewise, we have phosphide, sulfide, chloride, argon. We would have arsenide, selenide, bromide, krypton. And then here we would have antimonide, telluride, iodide, xenon. Same pattern. Because they have the same number of valence electrons. So these guys have 5 valence electrons. Actually, it just goes like this. 1 valence electron, 2 valence electrons. Now, scandium's tricky. Did I talk about scandium? We'll skip scandium for now. Over here we have 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 8 valence electrons, or 7 valence, I skipped 7. 7 valence electrons, 8 valence electrons. 8 valence electrons would be an octet that's filled there. Scandium, actually, how many valence electrons does scandium have? Scandium is a strange one. If we look at scandium, what's the electron configuration for scandium itself? Uncharged. So with the scandium, we work backwards. So let's start off with argon. I don't want to write all that stuff out. And so we start off with argon here. And then we go like this. This is 1, 2, 3, 4. So this would be 4s1, 4s2. It would be argon, 4s2. And then where's this? 3D1. Now, in terms of valence, we altered the ordering on this. This is the filling order, but we have this removing order or leaving order or losing order or whatever. This 3D1, 4s2. So spatially, the 4s electrons are further out. So if if the reason we have these 2 ways of writing this is how we generate it. We fill it. So this is the filling order. The filling order looks like this. For the orbitals, 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Are you starting to memorize this, basically? Yeah? So the filling order, how do I draw it? How do I draw it?
You draw arrows across.
Do I draw arrows across like this? Like that? Or could I draw diagonal?
Yeah.
Diagonal up or diagonal down?
Yeah.
This way? Other way? All right, that's right. So this is it. The 1s, 2s, 2p, 3s, 3p, 4s, 3d. And so this is it. This is that order here. And this is how we generate the electron configurations. But when they leave, when the electrons leave, you have an oxidizer coming on. And the oxidizer doesn't care about the energy. He typically cares about what's closest. What's closest. And so it turns out that the 3D is a little higher in energy, so it's probably easier to take that. Probably 3D electrons are probably easier to take, but the oxidizer is going to take the 4s because the 4s is right there. It doesn't have to dig around for the 3D, it just takes the 4s. So oxidizer comes along here, and it's going to oxidize the 4s before it oxidizes the 3D. Why? because it's. Hmm? It's easier to take because. Yeah, it's further from the nucleus. Typically, they're bigger orbitals. And so, in terms of removing, then we go this way. You know, we just remove it in that sense. This is going to be the losing order, or oxidation, or leaving. And so we're going to go from bottom up. And so sometimes what we want to do is we rank this numerically. And so the 4s are going to be taken before the 3Ds. The 4s come first. As far as losing. Losing, we're taking them off. Feel like we're going down. And so there are different ways we could do that. And so technically, how many valence electrons do we have here? And so when we look at it, it looks like there's only 2 valence electrons, because remember, these are core. The reason why the 3D are core is because they're inner shell, core inner shell. And if we look at the outermost shell, well, the outermost shell has the 3D in there, right? And so what we'll do is we'll say inner orbitals, because the shell's not really correct. Inner orbitals, let's go. This. Although the 3D belong in the 4s shell, right? And so this will be outer electrons, outermost. The outermost electrons are the valence electrons. And orbitals. So these are going to be the valence. But when we think about it, really the 3D, even though those are inner orbitals, meaning that they're closer to the nucleus, they're still susceptible to attack. And so something like scandium can go +2 if we lose those, or it can go +3 if we lose them. So scandium's a little weird. And so how many dots do you draw for scandium? How many dots do you draw for scandium? Well, for those noble gases, things get mixed up. You could say 3 or 2. It depends on what you want to do with the Ds. The Ds are susceptible to attack, maybe 2. What about iron? How many dots would you draw for iron? Iron's argon, 4s2, 3D, what? Iron. We count it 3D, 1, 2, 3, 4, 5, 6, 3D6. And then we'll rearrange the order maybe. Argon, 3D6, 4s2. We're going to lose the 4s2 electrons first. So iron +2 is no problem. Iron +2, we've lost those 2. But what about these 6 Ds? Well, we can lose one of them. We'll form iron +3. And so for transition metals, this is it. Okay, if we go with 3 dots for scandium, then maybe we should draw 8 dots for iron. But if we draw 8 dots for iron, is that done? No. Because if we draw 8 dots for iron, then to complete that shell, we need 18 dots, And so this is it. There's something called the 18 electron rule, which we're going to not talk about. What we're going to say is for transition metals, don't bother. Don't bother unless it's like pseudo, like silver. So yeah, silver we might be able to do one dot, you know, because silver is going to be argon. Actually, silver is krypton. Shouldn't have gone silver, but we'll do silver. So I wrote it up there. It's going to be krypton, 4s2. Oh, not 4, 5s2. Sorry, krypton 5s2, 4d9. Should be silver. Well, one thing we know about silver is this: it's one electron short from a filled D. One electron short from a filled D means we'll go krypton 5s1, 4d10. And then we're going to rearrange that order. It's going to go krypton 4d10, 5s1. And so what should we do? Should we show 11 dots? Or how many valence electrons does silver have? In this case, it's more clear cut. Silver is going to have one valence electron. The rest are going to be core. The 4d10 is filled. Scandium, on the other hand, if we applied the same to scandium, then scandium should have two valence electrons, but its charge is +3. And so this inner shell, or inner, I shouldn't say inner shell, this inner electron is going to be a reactant. And so, since this involves too much detail, we're not going to bother with the symbols for transition metals, so don't worry about it. In fact, even in advanced classes, you don't bother with Lewis, just for what we call main group. Now, what the main group is this. It's this S block and the P block. The D block and the F blocks of orbitals that are not included in the main group. So sometimes you'll encounter a transition metal, but we don't really apply the same way of thinking to it. But we can, well, calcium's main group, so we can do it for calcium. Let's take a look at calcium. Write the electron configuration for calcium ion. Well, I wrote the electron configuration for calcium metal earlier. And so I'll write the electron configuration for calcium metal. Calcium metal is going to be argon. Okay, tell me the rest. 4s2. So here it's clear cut, it's easy. We don't have to be ambiguous. How many valence electrons? 2. And so the Lewis symbol is going to look like this. Okay, what's going to happen to calcium? Is calcium going to gain or lose? It's easier to lose for calcium. So we're going to lose how many? 2. And so the way I show that is, okay, I'm going to have a calcium, and those 2 electrons are going to go, which are the dots over there. And then I'm going to put these brackets over here. So this is the Lewis structure for calcium 2+. This is something they forgot here in this table. In this table, this is the formula. These are formulas: sodium plus, magnesium 2+, aluminum 3+. But these aren't the Lewis structures or symbols. The Lewis symbols always have a square bracket around ions, like this. And then the net charge or the total charge is shown on the outside. Okay, what's the electron configuration for this? Probably should write it all out. Argon is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, if we lose those 2 valence electrons, then what are we left with? We're left with the argon core. That's it. In other words, we're left with 1s2, 2s2, 2p6, 3s2, 3p6. Filled first shell, filled second shell, filled third shell. filled shell configuration. Sorry. So we're going to have 18 electrons total, like argon. Oh, sorry, yeah, argon's 18. Take a look. Isoelectronic with argon. This is electron configuration with calcium. Core up to here, valence. Calcium ion to the left is core. Argon core. All right, why do we form ions? We form ions to make ionic bonds. Ionic bonds are this. So if I take sodium, let's just do sodium. How many valence electrons does sodium have? 1. And chlorine, how many valence electrons does chlorine have? 7. This is atomic chlorine, by the way. Chlorine's usually molecular, but for the purpose of this, it's easier just to look at it atomically. All right, what does chlorine want? Chlorine wants another electron, and then it's completed its shell. It's not kept, so it has a place. It can just take the electron off sodium here. If the electron gets taken off sodium, then we generate 2 ions. The sodium ion, which is going to have square brackets like this, and no valence electrons left. And the chloride ion, which is going to have 8 filled outer shell configurations, sodium chloride. Well, we form the ions, but that's not the end of the story. What we want to do is we want to form the compound. The compound is going to be this. It's going to be sodium and chloride. We need to make the bond to form the ionic bond. Well, where's that ionic bond? The ionic bond is here. This would be what we term the ionic bond. The ionic bond is just the electric attraction. That's all. Electric attraction. It's the ionic bond. So when we look at it, we don't just form one. This would be one ionic bond. We actually form a lot of ionic bonds. A sodium you can think of as a positively charged ball. And the chloride, it would be a negatively charged ball. So we'd have a sodium and a chloride like this. What holds the 2 balls together? The ionic bond. But if you have a positively charged ball, then all the negative balls want to bond to it. And so the negative balls are going to come like this. And so we don't just form one bond, we form, how many bonds are here? 4. But we don't just form 4 because this is 3-dimensional, so one bond can form up here with an ion that's stuck on the top. That's 5. And then one can come up from underneath. So if one comes underneath, then altogether, how many bonds do we have? 6. So in sodium chloride, you see 6 ionic bonds there. And so these are going to be 6 nearest neighbor ionic bonds. Well, the chloride's the same. The chloride is negative, so all the positives want to go around the negative like this. And so it turns out we can fit a total of 6. 4 in the plane, 1 above, 1 below. But if a positive comes in here, take a look. The nearest neighbor is negative, but the next nearest neighbor is positive. So sodium doesn't like the next nearest neighbor. It likes the nearest neighbor. It's good. But then, you know, that's positive, so a negative is going to come along here. And so this is called the next nearest neighbor. The next nearest neighbor, sodium likes. It's negative. But what do you think about the next nearest neighbor? The next nearest neighbor, does sodium like? No, sodium does not like the next nearest neighbor, and so on, and so on. And so what we have is we have what we call a lattice of bonds, lattice of ionic bond, in which you have to sum up the attractions over 3 dimensions and sum up the repulsions over 3 dimensions, and net it comes out favorable, and the lattice is usually strong. So in terms of energy, this is the way it works out. If I want to break apart this lattice, does that cost energy? Is it free? Or does it give you energy to break it apart? In other words, let's say I want to break the bonds in this meter stick. If I want to break the bonds in this meter stick, is that going to cost energy? Or is it free? There's no energy associated with it? Or is it going to give me energy if I break this meter stick? It's going to cost energy. And so when we break bonds, it costs energy. But when we form bonds, do you know what happens? It releases energy. And so the reason why we form bonds like this, the reason why we form a lattice like this is, you know, the ions are just going to keep attaching, and this crystal is going to grow bigger and bigger and bigger. Why? Because forming bonds is favorable. Forming bonds lowers the energy. Forming bonds releases energy. Now, if I break this and make smaller and smaller crystals out of it, that's going to cost energy. So if I take a large crystal of sodium chloride and break it up into smaller crystals, I'm going to be expending energy. And so the reason we form ions is so we can form bonds, ionic bonds. And it's not just one ionic bond. We want to form a lattice of ionic bonds in this crystal structure. That's going to release a lot of energy. And so this is why we form the ions in the first place. We form the ions in the first place to maximize. This is called maximizing bonding. Nature likes to maximize bonding. This is the formation of sodium chloride from sodium metal and chlorine gas. See all the yellow light there? It's a violent reaction. It's violent, meaning a lot of energy is released. It's hard to see it in this, so we can take a look at it here. It's a pretty short video.
A piece of sodium metal is placed in a flask containing yellow chlorine gas. The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
Do you see that white cloud? That white cloud is sodium chloride crystals.
A small piece of sodium metal is placed in a flask.
Well, anyway, you can see it here, sodium chloride formation. Oh, this one. Lonnie's lab.
We asked Lonnie to demonstrate the formation of an ionic bond. In this case, the bond between sodium and chlorine in sodium chloride. So Lonnie's filled a beaker with elemental chlorine. That's chlorine gas, Cl2. It's a yellow gas. He'll also use solid sodium metal. Solid sodium metal is a shiny silver metal that's very soft. You can actually cut it with a knife. Sodium metal is very reactive. It will react in air and water, so it's stored under hexane. He'll pull off a small chunk and immediately store it under hexane while he prepares the rest of the experiment. Now, to get the reaction to go, you'll want to clean.
Actually, this is not right. It's normally stored in mineral oil here. Mineral oil is an oil, and it's going to generate a lot of smoke if it catches on fire. So the hexane is to wash the mineral oil off. Now, the hexane is an organic solvent that is really good at washing oils and that type of stuff off, although it smells so great. And so he put it in the hexane to wash the mineral oil off. And hexane is somewhat volatile, so it'll evaporate and not generate too much smoke. It's,
The sodium, make the surface very clean, and warm it slightly to help the reaction proceed. They'll do that by placing the sodium in a spatula and then warming it over a flame to clean the surface and to get the sodium.
It's not cleaning the surface, he's evaporating the hexane with the heat. And then he's gonna get some kinetic energy in the sodium, and then we'll put it in.
Warm enough to initiate the chemical reaction. Now, the reaction between sodium metal and chlorine gas proceeds, but we know the ionization energy of sodium is greater than the energy released, the electron affinity, when chlorine accepts electrons. So the reaction goes because the positive ions formed on sodium and the negative ions formed on chlorine are drawn together, a Coulombic interaction, to form an ionic bond. The formation of that ionic bond, plus and minus charges attracted together, releases energy, and that's the driving force for this chemical reaction. And you can see that it's exothermic. Energy is being released. Bright red glow, typical of emissions from sodium.
Well, actually, most people call it yellow, if you look at the center.
Now, the reaction between sodium and chlorine, of course, forms sodium chloride. We typically know that as table salt. And Lonnie's prepared some in advance. He has white table salt, purified, that he can show us. There it is, purified in advance from Lonnie Laboratories. And Lonnie tells me the salt that he makes in Lonnie Laboratories is far superior to any salt that you can buy in the store. So what does he have to do now? Lonnie's going to demonstrate, clearly hasn't had his breakfast this morning, that Lonnie Lab salt far superior to any salt you could buy in the store. Thank you, Lonnie, for that demonstration that sodium chloride, an important spice and food flavoring. And when you make it yourself, the satisfaction is so much more complete.
There was that yellow light.
Is so much more complete.
And so I want to talk about the yellow light. The yellow light, we've seen yellow-orange light, street lamps. You can make light bulbs out of lots of different things. So we're going to go back a little bit to quantum and talk about the light bulb. If you make a light bulb out of sodium, this is what it looks like, the color here. It's a characteristic sodium lamp color. Kind of orange, yellow-orange light there. And what that is before the sodium reacts, it ends up getting excited. And when sodium gets excited, then electrons get excited, but they don't get excited to any energy. What do we call it? Is it a continuous spectrum or discontinuous? It's a line spectrum. And so it turns out for sodium, all these energies are forbidden. The only energies allowed is in the yellow region here of the spectrum. And so we just see this yellow light or yellow orange, or I don't really call it red because red is closer to the end here. This is Roy G. Biv going this way. In our book, Roy G. Biv, they have it flipped the opposite way. It doesn't matter, Roy G. Biv, if it's flipped one way or the other, or upside down, right side up. There is no right way. All we remember is red and violet, and then we know, where we are. And so violet's on the right, red is on the left. In your book, violet's on the left, red is on the right. No big deal. It's just a different way of just showing it. But anyway, red is way over here, so I don't really call that red. This is more yellow, in the middle of Roy G. Biv. But sodium is going to emit that. No other colors. It's weird. So that's the yellow light. This is before the sodium reacts to form the sodium chloride. Now, the success of quantum mechanics is we can describe this yellow emission line. Actually, if you zoom in on that yellow line, there's actually two yellow lines there. You can't really zoom in because the spectrometer that they use, spectrometer is what we do spectroscopy with. It wasn't very precise or a high precision machine. See, you could see yellow in the yellow region of the electromagnetic spectrum here. If we zoom in on that yellow, there's actually two yellow lines. Excuse me, right here, side by side. So at this wavelength, 500 something, 589 roughly nanometers of wavelength. The spectral emission lines. These are some other spectral emission lines. And so what's happening there is this. This is not the entire, what's this thing called? I think this is 3S, 3Ps. They don't show all the Ps. What is that? 3S, 3P, 4S. What's this thing called? Orbital energy level diagram. Although it looks a little weird because this is not the way I asked you to draw it. The way it's drawn here factors in a couple of other things. It factors in degeneracy and it factors in other quantum mechanical properties. So this is why it looks so funny. But it's a normal diagram. 3S, 3P goes to 4S to 3D to 4P to, we just follow that chart, the filling chart, whatever it is. But this one is made for electron transitions, so this is why it looks different. And these are the lines here. And so one of the yellow lines is a result of falling from this 3P down to 3S. So electron normally resides here. All the others are core. We have the core electrons, which would be, in this case, the neon core. So we're just looking at the valence orbital here. The electron normally is here. It can get excited to here. It gets excited to here. Actually, well, it's kind of tricky, because there's certain ways that are allowed and not allowed. But one thing is it can drop down. If it drops down here, it emits the 589.6 nanometer line. Or electron can get excited up here. If it drops from here, it emits a 589.0 nanometer line. This line here would be in the UV. These lines would be in the infrared, so you wouldn't be able to see those with that spectrometer. But this is it. So this is the success, of quantum mechanics. Because of quantum mechanics, we could better describe what's happening with the atomic line spectra. Bohr wasn't able to do this because if you look at the Bohr energy level diagram, it's very simple. It's not complicated like this. And so from that, why sodium street lamp? The sodium street, they don't take that much energy. It doesn't take that much energy to melt sodium. Sodium's easy to melt. It melts at about 100 degrees, less than 100 degrees C. And it's easy to vaporize because it's such a soft metal. So you vaporize it, and then it's easy to excite. It doesn't take much energy to excite the electrons in sodium. So these are very energy efficient lamps. This is why they put them off on the street. Does it make good reading light? No, but you know, at least you can see where you're going. And so you can make lamps out of many different things. Oh, the sodium lamps get very hot. We have a sodium lamp in the lab. We'll look at it. But you gotta watch out because they can emit UV, but you can put a UV filter there, so we don't get the UV. You can also emit infrared, but infrared, we're not gonna put a filter on that. For that. Okay, so why was so much energy released? That was one thing that was good about that last video. What was so much energy released in this? This is a highly exothermic reaction, and a lot of energy was released because we're forming a lattice of the bonds. And so this is why we even bother forming ions. Forming ions is just one step into forming compounds. We want to form ionic compounds. The more bonds we can form, the more stable things are, the lower energy. And so here we can see as the sodium atom has 11 electrons total. Out of those 11 electrons, 10 are core, 1 is valence. Here's chlorine, 17 electrons total, 10 are core, 7 are valence. And so chlorine is a powerful oxidizer. It wants to take electrons. So it's going to take electrons from sodium. So it takes an electron from sodium and forms chloride. Chloride is going to have 18 electrons now. It's going to fill that shell. And then sodium is going to lose it. And so we're going to be left with 10, where the core previously. Take a look at what happens to the size, though. You know, normally, which one's bigger, sodium or chlorine? Normally, sodium's bigger than chlorine, and that's what we'd expect because this is what we see. Let's go back to this old slide here, the last chapter. That's what we see here. Sodium's here, chlorine's here. So sodium is bigger than chlorine. Why is that? Well, shouldn't it be the other way? Because chlorine has more protons, more neutrons, and more electrons. So shouldn't chlorine be bigger than sodium? You would think it would be bigger, but it isn't. It's smaller. There's the same reason that helium is smaller than hydrogen. Why is helium smaller than hydrogen? The electrical forces, right? We have more protons. More protons are going to pull in the electrons with more force. And so it's like that science fiction tractor beam thing. You know, the more protons, it pulls it in. So it's going to pull in the electrons more tightly. So sodium has 11 protons. Chlorine has 17 protons. 17 protons, stronger attraction. It's going to pull in the electrons closer. And so the reason why is that it's going to get smaller because we have more protons. But there's a problem here because sodium has 11 protons. What about potassium? Potassium has 19 protons. So 11 versus 19. 19 protons should be even stronger. It should pull in the electrons closer. But why is potassium bigger? Because of the orbitals. Yeah. Not just the orbitals, but because of the shell of orbitals. And the outer orbitals, this would be a 3s, this would be a 4s. 4s orbitals are a lot bigger in general for a given thing. But there are other complications to that because orbital sizes change depending on how many protons you have. So do you guys remember this? Chart? Can you explain this to me? Yeah? You don't have to explain the blips, but Does it make sense overall? So, well, we'll just do it, repetition helps remember it, so you should repeat it yourself. But, hydrogen to helium, more protons, contracts, right? And then we add a shell, so it expands. Then lithium to neon, it contracts. Oh, this is ionization energy. I'm doing the wrong one. Well, ionization energy goes by size, right? And so size means helium's smaller, therefore has a higher ionization energy. So I'm looking at this, higher ionization energy is smaller. But maybe I shouldn't use this chart. This is how we explain the ionization energy chart. We explain the ionization energy chart like this. Helium's smaller, therefore higher ionization energy. Add a shell. Add a shell, the atoms get smaller and smaller as we go across because the number of protons increases. We're in the same shell until we hit max. Then we add another shell and it grows bigger. And so the same thing goes back here. Go across, more protons, smaller. Add a shell, it gets bigger. More protons, gets smaller. Add a shell, gets bigger. More protons, gets smaller. Add a shell, and so on. There are going to be blips. You see that? There be some blips in there, but otherwise, that's the general pattern. So the reason why it's so exothermic is because we're forming this lattice bonds. This is the sodium chloride lattice here. I know which one is which. The greens are what? Sodium or chloride? The greens. The greens are chloride. How could you tell? I could tell because of the size. I know the size of chloride. Chloride is bigger than sodium ions. What happens is this. Okay, so once you have this size down, then we have to add another series of sizes. The other series of sizes is for the ions. Take a look at what happened with the sizes of the ions. If we look at the size of the elements, okay, we got that pattern down. Now what just happened with the ions? That pattern just flipped, right? Because I just got done telling you chlorine is smaller than sodium. However, chloride is bigger than sodium ion. Why is that? Okay, well, this is the way I remember it. The way I remember it is I remember this size trend, and then I do this. If we form a cation, the general rule of thumb is when you form a cation, the size gets cut in half. And so the radius is half. And so the ion is going to be about half as big as the atom, the cation. When we make an anion, the size doubles. And so anions are about twice as big as their parent, and cations are half as big as their parent. And so that means the size chart, when you look for the ions, you have to visualize the size chart and then do that yourself. Meaning this. Well, you don't have to do it yourself because other people will do it for you. But what you have to do is you have to visualize this. If we form a cation, all of a sudden the size is going to be cut in half. And then when we form the anion, what's going to happen? The size is going to double. And so fortunately, there are charts that'll show you, So this would be the chart for the ions, but you don't have to worry about this. Or we kind of flip it. We flip it this way, but it still increases down. And so one way it's flipped, the other way it stays consistent. But beware, don't think the ions are going to have the same size as the parent ions. They don't. So that's what we see here. And so I know the greens are bigger, therefore these must be the chlorines. And the grays are smaller, therefore those must be the sodiums, the size flipped. And this would be a crystal here. So this is very strong. Have you ever tried to melt salt? Have you ever put some on a frying pan and tried to melt it? Has anybody successfully melted salt? No, I've tried, but not successfully. Wasn't able to melt it. And that's because it has a very strong lattice. Although you might think, well, how is it so strong? It's so brittle. It's easy to break. It's easy to break because of this. You know, the lattice itself is strong, but if you put a razor blade here and force the green down here, then who's the nearest neighbor? Here, the green's very happy because the nearest neighbors are all gray. But if you force this down a little bit, then it's going to be green and green. And green don't like each other, and what's going to happen? They're going to repel. And so these are easy to cleave. You get a razor blade, you can push down on it, and then it just breaks apart because now the nearest neighbors are like charges. It doesn't like charges. It likes opposite charges. There are a lattice. It's not just 6. Here it says 6 sodium ions surround each chloride, so, and vice versa. So if you have is that chloride or sodium right there, that green? That's a chloride, and then we have the 6 sodiums here surrounded. So that's 6 ionic bonds. But it's not just 6, you know, and vice versa. So if I look at the gray, there are going to be 6 greens for each gray. Here's a gray. There's 4 in the plane, 1 on top, 1 below this plane here. And so, same thing here. But what we have to do is, it's not just 6 and 6, it's going to be a whole lattice of bonds. And when we look at the whole lattice, we look at this, kind of this visualization here. This is a visualization, we draw lines here between the nearest neighbors, and then we can kind of see geometrically what the next nearest neighbors are. Then we can do a geometry calculation to calculate, you know, the distance, all that other stuff we want to do it. There's a mathematician, I think it was a mathematician or chemist or physicist who figured it out. He came up with a math-1 equation for calculating it over 3 dimensions, over a very large distance. You get the math-1 constant. But that's the sodium chloride lattice, and the sodium chloride lattice is strong, except if you melt it, you know, this is molten. This is not sodium chloride. Sodium chloride is not that easy to melt. Molten salts are like this. When you break apart the lattice, how do you know it's broken apart? It'll conduct electricity. Now the ions are free to move. If the ions are free to move, they'll conduct. So that's what a liquid is. So this can require very high temperature, high energy. All right, so we'll stop here. It'll take a break, and then